Hey everyone, and welcome to this explainer. Today, we are focusing squarely on exam prep for the NCP-MCI 7.5, specifically Section 7.2, Identifying Storage Savings Use Cases. So, if you're gearing up for the Nutanix Certified Professional Multi-Cloud Infrastructure exam, you are in the exact right place. I'm here to guide you through a really steady, in-depth walkthrough of Nutanix's storage optimization logic. We're going to break down exactly what you need to know to pass this specific section with a huge focus on how to match the right capability to the exact right workload. Let's get into it.
Here is our roadmap for today's scenario-based prep. First, why storage savings matter. Second, optimizing storage with examples. Third, exam traps and edge cases. And finally, key facts to memorize.
All right, starting right off with Section 1, Why Storage Savings Matter, Efficiency, Performance, and Exam Points.
Before we even think about looking at the mechanical configurations inside Prism, we need to establish exactly why Nutanix relies on these specific storage features in the first place. And to do that, we have to talk about the CVM, or the controller VM. Now, as an infrastructure admin, you already know the CVM is the absolute beating heart of our storage operations. It's the virtual machine running AOS that has to be active in the hypervisor to provide all that Nutanix-specific magic. But here is why this matters so heavily for your exam. The resources you allocate to the CVM directly dictate which storage savings features you can actually safely enable in a cluster.
We also need to quickly touch on VDI, or Virtual Desktop Infrastructure. Obviously, you know it's a technology that hosts desktop OSs on a centralized server. But why are we bringing it up right now? Because persistent VDI deployments are literally the primary textbook use case for some of the most aggressive storage savings features we have, which we'll dive into in just a second.
So the crucial point to remember is that understanding these storage efficiency capabilities isn't just about saving physical hard drive space or minimizing redundancy, though, yeah, it definitely accomplishes that, while boosting fault tolerance. It's really about matching the precise feature to the right workload. And that right there brilliantly illustrates exactly what the certification exam is going to test you on: scenario-based matching. You aren't just memorizing definitions. You have to fundamentally understand the why and the when to deploy them in the real world.
Moving on to Section 2, Optimizing Storage with Examples. Let's look at the mechanics and scenarios.
Let's see how this optimization actually plays out in real-world applications. The core differences between our big three technologies really come down to their ideal workloads and their timing. Think of compression as your everyday hero, your broad default. It acts inline or post-process and is fantastic for sequential I/O. Then you have capacity deduplication. This is your highly repetitive data specialist, doing heavy post-process work for things like persistent VDI and full clones. Finally, there's erasure coding. This is the heavy lifter for write-cold data. Think long-term archives, where it computes parity to save massive amounts of space.
Now, what's really interesting about how Prism handles this is the defaults. When you create a new storage container, Prism automatically defaults to inline compression with a 0-minute delay. Basically, this means the system compresses data immediately as it's written. It is your baseline optimization strategy for almost all license tiers, just silently working in the background to keep things lean.
Let's look at our first concrete example. Picture an exam scenario where you are tasked with rolling out persistent VDI desktops. First, you'd identify that you have highly repetitive, persistent data spread across hundreds of virtual desktops. Next, and this is absolutely critical, you verify your CVN meets the strict hardware requirements. Third, you enable capacity deduplication. And finally, you get to observe massive space savings as all those duplicate data blocks on your hard drives get consolidated down.
However, and this is a massive but, if the exam scenario explicitly states that you're using linked clones or Nutanix VAAI clones, you should not enable deduplication. Why? Well, because AOS storage natively manages duplicate data incredibly efficiently in those specific environments already. Turning on capacity deduplication there offers literally no additional benefit, and you're just unnecessarily burning your CVM's processing resources.
Okay, for our second example, consider a write-cold archive database. Here you're going to follow a totally different path. First, you identify the data as write-cold and read-heavy, meaning it's pretty rarely modified. Next, you have to ensure your cluster meets the minimum node count, which is at least 4 nodes for replication factor 2. Then, you enable erasure coding. The system goes to work computing a mathematical parity, represented as P, to replace those bulky, redundant full data copies. The massive benefit? Doing this can increase your usable capacity by up to a staggering 75%. It's a total game changer for archives.
Let's jump into Section 3.
Exam traps and edge cases. The gotchas.
Now we need to shift our mindset away from just deployment and focus on test strategy. Let's test your instincts for a second. What happens to deduplication if your scenario states that the controller VM only has 16 gigabytes of RAM? Whenever you see a question about enabling on-disk capacity deduplication, you must instinctively ask yourself about the underlying hardware environment.
The answer? It's a hard no. It simply won't be supported. The Advanced Admin Guide clearly dictates that Nutanix requires you to configure the controller VMs with at least 32 gigabytes of RAM and 300 gig SSDs for the metadata disk just to enable capacity deduplication. If your CVM lacks this strict threshold, on-disk deduplication is disabled. Period. Do not fall for a scenario that tries to sneak a 16 gigabyte CVM past you.
Here is another major trap they love to spring on you. We established earlier that inline compression with a 0-minute delay is the gold standard default. But what if the exam scenario specifically mentions a high CPU environment? If your environment has consistently high CPU usage, say over 80% on the CVM, or if it's highly sensitive to latency, you absolutely must change that default. In those specific cases, you need to select post-process compression and set a 60-minute delay to avoid burning too many CPU cycles. Keep that 60-minute number in your head. It is highly testable.
Furthermore, erasure coding is strictly bound by node counts. The exact thresholds you need to know are these. For replication factor 2, or RF2, you require a minimum of 4 nodes in the cluster. For replication factor 3, or RF3, you need a minimum of 6 nodes. Do not attempt to enable erasure coding on a 3-node cluster in an exam scenario. The system just will not allow it, and it's a classic trick question.
All right, finally, Section 4. Key facts to memorize. Your cheat sheet for the exam.
Let's bring the cognitive load down and really anchor these concepts. Memorize these 4 facts exactly as they are. 1. Deduplication requires a minimum of 3 nodes in the cluster, 32 GB of CVM RAM, and 300 GB SSDs. 2. Set your compression delay to exactly 60 minutes for high CPU or latency-sensitive workloads. 3. Erasure coding requires 4 nodes for RF2, 6 nodes for RF3, and is explicitly built for write-cold data. And 4. Do not enable deduplication for linked or VAI clones. So I'm going to leave you with this final thought. The test writers are going to try to bury these prerequisites deep inside incredibly complex multi-paragraph scenarios. But when you sit down in that chair for the NCP-MCI 7.5 exam, are you really going to let a 16 gigabyte CVM or linked clone slip past your radar? Armed with this explainer, I know for sure you won't. Good luck out there and keep learning.